Hello there, this is Coach Ikram, and welcome to this video on acids and bases. In this video, we're going to discuss theory. So we're going to start off by talking about the hydronium ion. So remember, hydrogen ions are not really free in an acidic solution. The water molecules are actually going to strip that hydrogen from the anion, and it's going to form the hydronium ion. This is what happens when you dissolve an acid in water. That water and that hydrogen ion are going to combine to form hydronium. So here we've got our acid, hydrochloric acid, reacting with the water, and you get hydronium plus your anion. As a note, hydronium and hydrogen are interchangeable. They mean the exact same thing. It's a concentration of the acid. And you're going to see both of these used throughout chemistry. So whichever one you see, just note that you could use the other to notate the same exact thing. So we're going to start by talking about Arrhenius' theory. An Arrhenius acid is going to ionize an aqueous solution to produce the hydronium ion or the hydrogen ion, whichever you prefer. So we've got hydrochloric acid, again, reacting with water to form hydronium and chloride. An Arrhenius base is going to contain hydroxide ions and ionizes in water to produce hydroxide. So we've got NaOH reacting with water to form the sodium ion, the cation, plus hydroxide. And then we've also got ammonia reacting with water to form ammonium and hydroxide. So they both form that hydroxide ion, which is the definition of an Arrhenius base. So if I was going to classify each of these, they're already written out, but we can just kind of go through it. We've got calcium hydroxide. That's going to be an Arrhenius base because it's going to donate this hydroxide to the solution. HBr is going to be an acid because of that hydrogen. It's going to donate that. H2SO4, sulfuric acid, this hydrogen will be donated to the solution. And then Arrhenius base, this OH. So it produces hydroxide in solution. Some disadvantages to Arrhenius' theory. They can only be applied to reactions that occur in water. And you can actually have acid-base reactions that occur in the gas form. Some bases, such as ammonia, don't actually contain hydroxide ions. They're formed when they contact the water. That's something that happens when it reacts with water. So the Arrhenius theory doesn't always apply to everything, which brings us to the Bronsted-Lowry theory, which we're going to start by talking about the hydrogen ion. The hydrogen ion, we talked about hydronium, we talked about hydrogen, but we can actually call it, it's a proton. Hydrogen ion contains a single proton and an electron. So when it loses an electron, all that remains is that proton. Hence, hydrogen ions are often referred to as protons. And we're going to use that when we're talking about the Bronsted-Lowry theory. And it's sort of more or less the update on the Arrhenius theory. So in the Bronsted-Lowry theory, substances are going to be defined by their actions. It's all about the exchange of that proton. So if you look in this little diagram, you've got your acid and your base. The Bronsted-Lowry acid is going to be the reactant that donates the proton. So acids donate. They give up that proton. And then your Bronsted-Lowry base is going to be the reactant that, instead of talking about in terms of that hydroxide, it's actually going to be the acceptor of that proton. So everything here is in terms of that proton or that H+ ion. So again, if you look back up at this drawing, we've got HCl right here. And that's our acid, hydrochloric acid. We've got water, in this case, acting as the base. So you notice that hydrogen from the HCl is gone over here. It left, so that must be our acid because it donated that proton. And then our base went from H2O to H3O plus hydronium, so it accepted proton. Hence, HCl is our acid and water is our base. So continuing with Bronsted-Lowry theory, once you take the proton away from the acid and give it to the base, you're actually going to come up with two conjugates. The Bronsted-Lowry conjugate acid is going to be the product that forms after the Bronsted-Lowry base accepts its hydrogen. And the Bronsted-Lowry conjugate base will be the product that forms after the acid has donated it. So the base becomes the conjugate acid and the acid becomes the conjugate base. So if we're looking at it visually, we've got a reaction up here drawn in Lewis dot structures. So if you note, what I like to do is kind of look and see, always look for that proton, always look for that hydrogen and see what's happening with it. So in this case, I've got a hydrogen here. Let me pen. A hydrogen here, and you notice over here, that hydrogen is gone. So this compound was my acid. Okay, it loses my proton, my hydrogen ion. And so this over here then is going to be my conjugate base. And I see those two as partners. I'm going to draw a line to show that pair. Then I've got water right here, and in this case my water has only 2 hydrogens on the left, but on the side it becomes hydronium and has 3, so that means it collected that proton. It added that proton to it, so this must have been my base, because that's what bases do, according to Bronsted-Lowry, and that makes my conjugate acid. So my base and conjugate acid pair right here, I can draw with a line. So to recap it, which reactant loses the proton? That's going to be my acid, which we labeled, and its partner is going to be my conjugate base. Which reactant gained? That was my base, and its partner is my conjugate acid. Remember, your conjugates are always the products. Your acid and base are always the reactants. So, Bronsted-Lowry conjugates. When we are discussing kind of sort of what makes what, strong acids are always going to make weak conjugate bases. And weak acids are always going to make very strong conjugate bases. So they are going to be opposites. Okay, so an amphoteric substance. An amphoteric substance is going to act as an acid in some cases. So that means it's going to donate that proton. And sometimes it's going to act as a base, and it's going to accept that proton. And it all just depends on the situation that it's in. Good example of this is water. Remember, in the self-ionization of water, what was actually happening there was those 2 water molecules, one was acting as my acid and one was acting as my base to form hydronium and hydroxide, conjugate acid and my conjugate base. And ammonia, excuse me, is going to do the same thing. So how protic is it? When we're talking about acids, they can be defined by how many hydrogen plus ions they donate. And this is simply a notation. I'll make it so we can see the whole chart. So for example, a monoprotic acid has, as you would imagine, 1 hydrogen proton to give. And an example of that would be HCl. It only has that 1 hydrogen. A diprotic has 2. An example of that would be H2CO3. Triprotic, 3. An example of that is phosphoric acid, H3PO4. And how basic is it? The same thing we just did with acids. We can also label our bases in the same way. They can be defined by how many protons they'll accept. So we have monobasic. I don't know what that's there, but this is going to be monobasic. Dibasic and tribasic. So monobasic would have 1 proton to collect. So for example, HSO4 -1. Dibasic would have 2, CO3 2 negative, and tribasic would have 3. And remember, this is all basically saying how much room do I have for hydrogens to be added? Do I have room for 1? Do I have room for 2? Do I have room for 3? We can compare solutions by type and relative concentration. So when I'm talking about acids and bases, I can compare them by their molarity, their concentration, or if they're strong or weak. So in this first case, I've got 0.1 molar of HCl and 0.1 molar of HBr. They're both strong, and they're also both the same concentration. So that's that. In the second one, though, I've got 2 strong acids, but one of them, the HBr, is more concentrated. Third one, I've got HCl is strong. They're both the same concentration, but HCl is strong and acetic acid is weak. And then the last one, that is citric acid. So that's more concentrated than my phosphoric acid, but they are both weak acids. And it's important to note that weak acids can still be dangerous. They're not, just because it doesn't all completely ionize in water does not mean that it can't harm your skin. So it's important when you're discussing and looking at acids, particularly in a lab, that you note both the strength of the acid and also its concentration. So now we're going to talk about acidic and basic salts. Acidic salts are formed when a strong acid and a weak base react. So for example, aluminum chloride. If I formed aluminum chloride, my parent acid of that was HCl, and my parent base of that was aluminum hydroxide. That should make some sense. We've got HCl plus aluminum hydroxide, and that's going to form aluminum chloride plus water. So that's what I did, was I basically took my salt and said, well, my cation is now paired with my hydroxide, and my anion is paired with my hydrogen. That's how I found my parent salts for that, or my parent acids and my parent bases. If I have an acidic salt, because I had a stronger acid and I have a weak base, my pH is going to be greater than 5 and less than 7. So slightly less than 7 instead of neutral. When it's placed in water, it's going to form an acidic system. A basic salt is going to be formed when a weak acid and a strong base react. So for example, if I've got acetic acid, that's a weak acid, and my parent base is lithium hydroxide, that's a very strong base, then I'm going to have a slightly basic salt, and that's going to have a pH greater than 7, but less than 9, so slightly above neutral. Neutral salts, though, are formed when you've got a strong acid and a strong base. So, for example, lithium chloride was formed from HCl reacting with lithium hydroxide, and those are both strong acid, strong base, and you'll get a neutral salt, and it should have a pH of 7. So we're going to go ahead and fill this out to look at this. So I've got my NaNO3, and remember, my cation's always going to bond with my hydroxide. Let's get my pen up here. And my anion is always going to bond with my hydrogen. So that's how you build your parent acid and your parent base. So in the case of NaNO3, my parent acid is going to be HNO3. That is a strong acid. And my parent base would have been NaOH. And that is also a strong base. So if I do the double displacement reaction between the two of those, I get NaNO3 and water. And my predicted pH of that, because it's strong and strong, it's a neutral salt. And so my pH should be 7. If I've got iron 2 sulfate, my parent acid is sulfuric acid, H2SO4. That's a very strong acid. Then I've got iron hydroxide as my parent base, which is a weak base. So that's going to be an acidic salt, because I've got a stronger acid and a weak base. So in my acidic salt, my pH is going to be between 5 and 7, slightly lower than neutral and slightly more acidic. If I've got calcium phosphite, my parent acid is going to be H3PO3. That's a weak acid, but my base is calcium hydroxide, and that is a strong base. And so my predicted pH is actually going to be between 7 and 9, and that's going to be a basic salt. That concludes our acid video on theory and concepts. Hopefully you took high quality notes, rewatch this video as needed, and ask questions in class. Thanks.